Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2018 physics paper short answer questions part 2, where we'll be basically going through, I believe, question 11 to question 20. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Perfect. Question 11. Figure 13 shows two speakers, A and B, facing each other. The speakers are connected to the same signal generator or amplifier, and the speakers are simultaneously producing the same 340 Hz sound. Take the speed of the sound to be this, calculate the wavelength. Easy. So, we know that velocity is equal to your frequency times your wavelength. So basically your wavelength is basically your velocity over your frequency. Now we know the velocity is what? 340 divided by your wavelength, which is what was your wavelength? Sorry, your frequency, sorry, 340. So your wavelength is basically 1 meter. So 1.0 meter. Easy. A student stands in the center, equidistant from speaker A and B. He then moves towards speaker B and experiences a sequence of loud and quiet regions. He stops at the second region of quietness. So basically he stops at the nodal, means where basically destructive interference happens at the second, where n basically equals 2. How far has the student moved from the center? Explain your reasoning. So basically what the student was, is he was in the middle, basically. He was in the middle, and of course in the middle, where he's equidistant from A and B, he's gonna 100%, he's gonna hear antinodal, so he's gonna have constructive interference there. And so basically he moves to the right, they said to B, basically, yeah? He moves to speaker B. So basically he moves to the right. He moves to some distance here. Let's say this distance. At some distance here, to the right. And he right now at that position, he hears a second region of quietness. How far has the student moved from the center? So what I would do basically is think, all right, what I'm going to first is find the path difference. Because I know it's a destructive interference, I can easily find the path difference. So we know the path difference. Path difference is what? M minus half lambda. So we know that basically it's the second. And our lambda, which is 1 meter, basically, which is just 2 minus a half, which is basically 1.5 meters. That is your path difference. So basically, so if he's here, basically right now, and his path difference, which is the distance of basically of A, so this distance, let's say this distance to this distance is called Y, and basically this distance to this distance call it X. Basically, your path difference, your P of D, is equal to basically Y minus X, because it's basically the difference between the the speakers, the distances from those speakers. And so I'm trying to think. All right, I know 100%. This is what we need to calculate, basically. How long has he walked from the center? Now, what do I know? So I'm trying to think. So what do I know that will give me this hint? Alright, I know I can actually rewrite X, this X. I can write X basically as what? I can rewrite X as 10 minus Y. Isn't that true? Because if I know this whole length is 10, and I minus this part, I minus this part all the way, I'll leave with X. So X is equal to that. So I basically have just created a formula. So if I know path difference, so P of D is equal to Y minus X. And I know X is equal to this. So I'm going to sub it in there to the X, basically, which is 10 minus Y. I can solve for Y, basically. So, because I know path difference is 1.5. So it'll be Y minus 10 plus Y. So 1.5 is equal to 2Y minus 10. So basically, what is, so it's going to be 1.5 plus 10 and divided by 2. So I've already calculated Y. So Y is basically now 5.75 meters. So let's come back to this and understand what's happened. All right. So let's rub these out. So I found that the distance basically from here is 5.75. Basically from here to here. I know this. I know this is the center, which is basically 5 meters. So what do I know? This rest of this has to be 0.7, pretty much 0.75 meters. So this distance from the center, because you know how the total here is basically 5.75. I know that, you know, halfway through this is 5. So this rest of this must be 0.75 basically. So we've basically just calculated, yeah, the distance. So 0.75. There's a lot of maths. I just basically I just use some basic maths here, but yeah. Wow. I hope that's right. Perfect. Question 12. Optical fibers are constructed using transparent materials with different refractive indices. Figure 14 shows one type of optical fiber that has a cylindrical core and surrounding cladding. Laser light of wavelength of this is shown from air to the optical fiber. All right, beautiful. Calculate the frequency of the laser light before it enters the optical fiber. Easy. Now we know, again, velocity is equal to your frequency times your wavelength. So we want to calculate the frequency, which is basically your velocity over your wavelength. Now velocity, because it's basically a laser light, it's going at the speed of light. So 3.0 times 10 to the power of 8 all over your wavelength. So what is your wavelength? They did tell us, yeah? 565 nanometers. So 565 times 10 to the power of -9 to get it in nanometers, basically. And that's going to give me my answer. 565 times 10 to the -9. So basically, I get 5.3 times 10 to the power of 14 hertz. Easy. Have I made any mistake? Looks good. Yep. Next question. Calculate the critical angle for the laser light at the cladding core boundary show you're working out. So basically, now it's inside here, where it's core, and it hits a boundary where you can see it's totally internally reflected. But if we want to calculate basically the critical angle, basically this here, if I draw a normal line here, if I draw a nice normal line here, this is the angle that we're trying to basically calculate, this critical angle. And to do that, it's very easy. We know the formula for critical angle. So N1 sine theta C is equal to N2. Where are we going from? Well, we're going from the core to the cladding, basically. So N1 is going to be your core, basically. 1.67, is that right? Sine theta C is equal to N2, which is your cladding, which is 1.45. Basically, your theta C is what? It's basically your sine inverse of 1.45 divided by 1.67. So that's going to be basically 60.3 degrees, basically. Nice. Question C. Calculate the speed of the laser light once it enters the core of the optical fiber. Give your answer correct to 3 significant figures. So let's come back here and rub this out. We don't need this. So as it's coming basically from the air, as you can see, and now it hits the core, what are we going to know? Well, of course, basically its speed's going to decrease because, you know, when it's going to core, there's a high refractive index, so your basically your velocity decreases. And the way we would do that, calculate the velocity when it's in the core, is basically using, let me write that down. So N1, basically N1 V1, N2 V2. So N1 is basically we started coming from the air at a velocity of what? Basically at the speed of light. We would come at the speed of light when it's in the air. So N1 is 1 and V1 is basically the speed of light. N2 is basically when it's in the core, which is 1.67. Yep, 1.6 is at the core. Yep, and then V2. So basically now we can calculate what is V2. Let's calculate that. Let's make it our speed. And that gives me basically 1.8 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. Is that right? 7? So 1, 2, 3, 4, 5, 6, 7, 8. 8, my apologies. Yep. So 1.8 basically. 1, 2, 3, 6, 7, 8. Beautiful 8. Easy. Cool. question 13. Physics students studying interference set up a double slit experiment using 610 nanometer laser, as shown in figure 15. The light power output of the laser is this much. So basically what it's saying is it releases, this is how much light. So it releases 5.03 times 10 to the power of negative 3 joules every second, so per second. So every 1 second, it releases this much energy. Calculate the number of photons leaving the laser light each second. So this is how much in total each second they're leaving, how many energy or energy of photons that are leaving. So we just need to basically calculate how much one photon, how much energy does it output, basically. How much does it release? So to do that, looking at my formula sheet, all right, so let's look at this. All right, so the energy of a photon is basically given, because I know the wavelength, so I can use that. So energy of a photon is basically what? Hc over wavelength. So basically what I want to do is, what's our h? It's basically, look at my formula, so it's 6.63 times 10 to the negative 34. Times your speed of light, which is 3.0, times 10 to the power 8, all divided by your wavelength, which is 610, so 610 times 10 to the negative 9. Is that right? Yes, so that's going to give me 610 times 10 to the negative 9, and that gives me, basically, it releases, so every photon, each photon releases this much energy, basically. Joules. This is how much each photon basically releases. So if I know every second that we're releasing this much energy, we just need to divide this by this to know how many photons are being released to make up this energy every second, basically. So what we're going to do is basically, what's 5? Let me write that nice. 5.03 times 10 to the negative 3, all being divided by 3.26 times 10 to the negative 19. So that's going to give me, yep. And that basically gives me 1.54 times 10 to the power of 16. They're a number. You don't write joules. There's no unit for number. And yeah, that's basically it. Beautiful. A section of the interference pattern observed by the student is shown in figure 16. There's a bright band at point C, the center point of the pattern. Of course there has to be, because basically it's equidistant from the slits. Explain why point C is in the bright band rather than the dark band. This is one of the most easiest marks to get. I've seen it in so many of those old past exams, and it's one of the easiest to get. Basically, what you just need to say is that the path difference is 0 at the middle, because it's equidistant from each slit, and hence, if your path difference is 0, constructive interference happens there, and therefore that's why it's a bright band than a dark band, basically. So let's write that. So we can say the path difference is 0. Is 0 as it's equidistant from each slit. Hence constructive interference happens at C. That's basically it. That should give you basically that full marks there. Nice. Another point on the pattern to the right at point C is further from S1 than S2 by a distance of 2. Basically, this is just your path difference, because it's saying it's another point. So let's say it's this point, basically. So it's saying, and let's say this is the source. Let's call this S1. Oh, wait, which one's further? Wait. another point to the, well, basically to the right. So let's say pick one. Let's pick one random. So let's say it's this point here. That's another point on the right to the is further away from S1. Further away. So this is S1 here basically. That's your slit, and that's S2. And by distance of this. So remember your path difference. What it is the difference between these, the distances between the sources. And that's what it's saying. So further from by distance of it, this means that this is your path difference. I think that's what will confuse a lot of students. They didn't say path difference, but it basically means this is your path difference right here. Mark this point in figure 16 by writing an X above the point. You must use your calculations to justify your answer. Let's do that. So what I'm going to do is, because I know the path difference, there could be a possibility that it could be both a constructive interference, so it could be a bright band, or it could be a destructive interference. So the way that I would determine this is by basically writing two formulas. So path difference could be, so this path difference could be, constructive interference, or it could be destructive interference. The way you would determine it is by the n value, basically. So let's try the constructive interference. So sub that in there. So 2.14 times 10 to the negative 6 and divided by the wavelength. What is our wavelength? And that's going to give us our n. What's our wavelength? Didn't I tell it? 610 nanometers. So 610 times 10 to the negative 9. That gives me 3.5. Look at the answer. N has to be an integer, so it has to be a full number. Why is it 3.5? That tells me it's not a constructive interference. It must be destructive, because if you did the same thing here, so if you put the part and divided by your lambda, like what we did here, you get n minus half equals 3.5, and you bring that half to the other side, and you get basically 4. N equals 4. So we know it has to be a dark band. Basically, it has to be a dark band, and yeah, so it has to be a dark band, and at n equals 4, it occurs. So basically, if you want to remember, this is basically 0. So that's 1, 1, 2, 2, 3, 3, 4, 4, 5. So basic, it's dark. It's a dark band, and it occurs at 4, n equals 4. Basically, it has to be this one over here. Let's write that down there. Yep, so because 1, 1, I want to make sure everything's done. 1, 1, 2, 2, 3, 3, 4, 4. Beautiful. So it's this one over here. That's where your X should be, basically. And let's rub these out. Done. I want to double check. So I want to double check. N equals 4. So, yep. So 1, 2, 3, 4, 5, 6, 7, 8. Yep. Does that look good? Have I made any mistakes? N equals 4. 1, 1, 2, 2, 3, 3, 4, 4. Yep, 5 then. Easy. Done to right, further ST. Beautiful. That is it. That's it. We've kind of labeled it. Do we label it? Mark the point on figure by writing the X above, and you must use calculator to justify your answer. We have justified our answer, basically. Yeah. Perfect. Question 14. Let's have a look at this. Janie is stationary in a spacecraft traveling at constant speed. Okay. Does this mean that the spacecraft must be in an inertial frame of reference? Justify your answer. So for something to be in an inertial frame of reference, it must be non-accelerating. So the problem is constant speed. No. It needs to say constant velocity, because even though you might go at constant speed, you might be still accelerating if you're going in a circular. For example, if you have things that go in circular, let me write this. So if you go basically something that goes in basically circular motion, something like that. Now, it has constant velocity. We know stuff like this basically have constant velocity. Its velocity is constant, but guess what's happening? The direction is changing, meaning what? Your velocity is not constant, basically. Yes, your speed's constant, but your velocity is not constant, meaning if your basically velocity is changing because of the direction, there has to be acceleration, and that's why it's always towards the center. So there is actually, it's not an inertial frame of reference because there is actually accelerating. It is accelerating, so be careful of that. Having constant velocity, constant speed, basically, doesn't mean that you are in an inertial frame of reference. Beautiful. So let's write that down. So we're going to just say basically nope. So no, the velocity may not be consistent. So may not be, maybe not constant. What am I saying? No, maybe. So no, the velocity may not be constant as the spaceship could be moving in circular motion where there is acceleration. Hence no inertial frame of reference, basically. Basically, that's it. Nice. Question 15. A stationary scientist in an inertial frame of reference observed a spaceship moving past her at constant velocity. Okay, that's good. She notes that the clock on her spaceship, which are operating normally, run 8 times slower than her clock, which are also operating normally. The spaceship has a normal has a mass of this. Calculate the kinetic energy of the spaceship in the scientist's frame of reference. Okay, let's think about it again. I want to understand. So a stationary scientist, so basically let's say this is a scientist here. In an inertial frame of reference, observed a spaceship, so let's say this here. Or let me draw it like this. Maybe this is our spaceship, basically. It's like a big, yep. Moving past it at a constant velocity. So basically, this thing is moving. She notes that the clock on the spaceship, which are operating normally, run 8 times slower than hers. Of course, so basically we know that when the spacecraft's moving at high velocities, we know that it's going through left contraction. So it's going to be measuring basically proper time, and she's basically going to measure the dilated time, basically. We've also learned that, yep. So what do I know is because we know that the proper time is, so this here, it's the time that's dilated, so it's actually quicker. Her one's actually going quicker, and this one must be slower because this is the real time, but her one's being dilated. So it's basically for her, she's like, why is their one running slower than hers? But because her one's actually running faster, that's why. Yep. All right, calculate the kinetic energy of that. They've given us here. It runs 8 times slower. We can actually use that because that tells us our gamma or our Lorentz factor must be 8. Think about it. So we know that the time dilated is 8 times your proper time. So here so if this proper time is slower, to compensate that, if you're going to multiply that with 8, because it's 8 times slower, that's her time. So basically, yeah. So it must be basically, that's your lambda, basically. We know our lambda, basically, it's 8. And we can easily calculate the kinetic energy of a spaceship in the scientist's frame of reference. We know that kinetic energy is lambda minus 1, basically. So minus 1 is equal to, mc squared, basically. So our lambda is 8, so it's going to be 7. Mass of the spaceship, which is 10,000. And c squared, which is 3.0 times 10 to the power of 8 squared. I'm going to double check if I've written it right. Looks good. So basically that's 6.3 times 10 to the power of 21 joules. Beautiful. Question 16. Quasars, I don't even know how to say that, are among the most distant and brightest objects in the universe. One has a brightness that changes rapidly with time. Scientists observed that the quasar's brightness over a 20-hour time interval in the Earth's frame of reference. The quasar is moving away from the Earth at this speed. So basically, okay, imagine this is the Earth. I always try to draw diagrams to know which one's like, dilating. And so basically, this is the Earth, and basically this is the, I'm going to draw another local ball. And this is quasar basically moving away from the Earth at some velocity, at a high velocity. So this is her. Moving at a velocity of, what was it? And moving at basically 0.704 c. Now, let's think about it before we do any questions. I know that if quasar is moving at such a high velocity, in its frame of reference, it's going to see left contraction. We know that. It's going to see length contraction. It's going to see its length that's in front of it being contracted. So then this must be measuring your length, your proper length. So if this measure basically, yep, and this must be hence measuring your proper time, and this must be your dilated time. So basically our Earth is basically measuring your dilated time, and this one here must be your proper time. So calculate the time interval that would be observed in the Quasar's frame of reference. So the time, this one. So if she, by the way, they're going to be measuring your proper time. So what we want to try to calculate is your proper time. So we know that basically proper time is what? It's your time dilated over your gamma. Is that right? Yes, it is. So, yeah, your proper time, your dilated time is the one that's been measured by the Earth. And we have that, don't we? Yep, measured by the Earth's frame of reference, which is 20 hours. And we want it in hours. So it's going to be basically 20 over 1.41, basically. So that's going to be basically just 14.2 hours. Done. Question 17. To investigate the photoelectrical effect, Sai and Kim set up an experiment. The apparatus is shown in figure 17. Beautiful. When the light source on a filter is in place, Sai and Kim measure the maximum kinetic energy of the emitted photoelectrons by gradually changing the collector voltage until the current measured by the ammeter just falls to 0. They just record this voltage, the stopping voltage, for each frequency of the incident light and plot the results in a graph of the stopping voltage versus frequency, basically, of the incident light as shown. Beautiful. With 6.0 times 10 power of hertz light, the ammeter always shows 0. Sai wants to repeat the experiment for this frequency with a much brighter light source and wants to expose the metal to the light for much longer. Kim says photoelectrons will never be ejected with this frequency. Basically, Kim's right. First of all, what he's doing wrong is if so it says the ammeter always shows 0 because it basically means that there's no electrons being emitted, or there's no photoelectrons being let out. So Sai wants to repeat the experiment by basically for this frequency by basically with a much brighter light, and wants to expose it much longer. That's not going to do basically anything if you do that, because you still have. So yeah, wait. So it says with this frequency, the ammeter always shows 0. Sai wants to repeat the experiment for this frequency with a much brighter light source and wants to expose the metal to the light for much longer. No, it doesn't depend, on much longer. Kim says the photoelectrons will never be ejected with this frequency. Basically, Kim is true. They will never be ejected with this frequency. Who is correct, Sai or Kim? Right answer. Kim, basically. Easy. What explanation might Sai give to support her opinion that by waiting longer and using a brighter light source, photoelectrons could be ejected from the metal with a light frequency of this? So look, Sai has she's thinking in terms of the basically the model, the wave model. Basically, she's believing that basically, let's say this is the electron here. This is what she's believing. She's believing that she's believing that a wave, what it does is if you let it longer, if you leave it longer, it's going to have more energy. These waves will carry more energy. And basically, she thinks that it's going to hit the electron, basically. It's going to hit the electron and just keep on doing that. So more waves hitting it, and this electron's basically going to gradually increase. It's going to absorb so much energy until it gets released. That's what she's believing, which is what the wave model basically predicts. That's how the wave model thinks. But that's wrong, because the photoelectrical effect, that's what it shows, that it proves that it's wrong, because there is, so straight away that's wrong. So that's what she's believing. So basically, so what explanation might Sai give to support her opinion? By waiting long, using a brighter light, photoelectrons could be ejected from the metal with a light frequency. So what she's saying is basically Sai believes that, brighter light actually just carries more energy, and so the electrons will absorb that. And so she said also by waiting longer. So when she's waiting longer, she's thinking that that more of the energy will be absorbed by the electrons by waiting longer. That's what she's thinking. So it will be more emitted, which is wrong, basically. But that's what she's believing. So let's write that down. So Sai basically believes that a brighter light carries higher energy for electrons to absorb, basically. So waiting longer allows the electrons to absorb enough energy to be emitted, basically. That's what she's believing. That's what basically the wave model predicts, which doesn't explain it. It doesn't work that way. So yeah, is that right? I just want to double check with this light. The ammeter always shows 0. So I want to repeat this experiment for this frequency with much brighter light source, and wants to expose the metal to the light for much longer. Kim says that photon will never be ejected. Basically, yep, that's correct. That looks good. Using the graph to calculate the Planck's constant. Easy. Let's do that. So what I'm going to do is basically I'm going to draw a straight line that passes through these points. I'm going to draw in red. So I'm going to first draw just a nice line that passes through all these points. And I'm going to just continue off. That looks like it. Sorry, it's going to look like this, basically. That's going to basically move. It needs to be basically parallel like that. Alright, and so also, so like that. Beautiful. That's perfect. So that's that. So remember, to find Planck's constant, it's just basically what's the units? Electrovolts per second. So basically, Planck's constant is just a gradient of a line, of this line. So I'm going to pick 2 points that are the easiest to see. So this point looks great, to be honest. It's on the graph, and I'm going to estimate, let's say, this point here, basically. So your Planck's constant, which is basically h, or your gradient, it's basically 0 minus, so I'm going to say 0 minus negative 1.5, basically. All being divided by, that's a difference, so 7 minus 4. So 7 minus, is that 7 minus 4, was it? Yes, it is. So 7, basically 7 minus 4 is, so 3, and what's it times 10 to the power 4? Is that right? So times 10 to the power 14. Times 10 to the power 14. Yep, so 7 minus all of that. And that should give me my answer. 1.5, basically. 3 times 10 to the power 14. Basically gives me 5.0 times 10 to the power of negative 15 electrovolts, basically. That looks correct for my sense. So 7 minus 4, yep, that's 3, and yes, so 1.5. Yes, that looks good. So done. Determine the work function of the metal from the graph, give your answer and reasoning. So basically the work function is just the y value. And basically just look at the y value here. It approximately is, I would say, like, 3.6, basically, 3.6 electrovolts. 3.6 electrovolts. Oh, it's already, and give your reasoning, the y value. The y, or basically just, why don't we just say where it crosses the, yeah, just the y value, the y value of the graph. Beautiful. Just is the y value. Done. Question 18. The diffraction pattern for X-rays and electrons through thin polycrystalline aluminum foil has been combined in the diagram in figure 18, which shows an electron diffraction pattern on the left and an X-ray diffraction pattern on the right. The images are in the same scale. The X-rays have a photon of energy of that. Okay, basically you can see that they both have the same wavelength. Look at the pattern. They actually look very, very similar. And so we know that basically, why is that? Why do they have basically the same pattern? Don't forget, wavelengths are the same, and also momentum is the same. Calculate the wavelength of the electrons in nanometers. So basically we just have this information, which is the energy of the photons. So what I'm going to try to do is basically get the momentum, because the momentum is the same for both. But remember, the energy is different. Don't equate energies and stuff. So what I'm going to do is basically looking at my formula sheet. What I want to do is, okay, I know that energy of a photon, so energy of a photon looks like it's P, your momentum times your speed of light. So basically, if I want my momentum, it's basically your energy. Make sure, but it's in electrovolts, so you want to make sure it's in 8,000. Make sure it's converted to joules, so 1.6 times 10 to the negative 19, basically. Yep, so that electrovolts, so times 10 to the power 19, and then multiply by the speed of, divided by the speed of light. That's going to give me the, basically, momentum. So that gives me, wow, a very small number, but our momentum has come out to be 4.26 times 10 to the negative 24 kilograms per meter second. So we got that momentum, basically. And so what I'm going to do with that momentum is, I know momentums are the same, so I can go to the electrons. I can equate it. Yes, so I know that wavelength is going to be basically h over momentum. So basically, I know that h is what? So h is, we want it in basically, yeah. So 6.63 times 10 to the power of negative 34. All being divided by your momentum, basically. Which is basically 4.26 times 10 to the power of negative 24. Looks good. 6.63 times 10 to the negative 34. Like that. So I overall get, make sure it's in nanometers, so I'm going to times it 10 by to the power of 9. I get basically 0.15, basically 155. Easy. Calculate the kinetic energy of the electrons in joules. Show working out. So we know that, okay, so we want the kinetic energy of the electrons. So we know that kinetic energy is basically, we can write it as momentum squared over 2 times the mass of the, what we call the electron. So if I know the momentum initially was what? So momentum was 4.26 times 10 to the power of negative 24. And I want to make sure square it, sorry. And divided by 2 times the mass of an electron. So the mass of an electron is basically 9.1 times 10 to the negative 31. I want to double check that. Yep, that looks good. So that should give me the amount of energy, if I'm not mistaken. No mistakes. Yep, so 4.26 times 10 to the negative 24. Square that. 2 times 9.1 times 10 to the negative 31. That gives me basically, basically just 9.97 times 10 to the negative 18 joules. Yep, that's easy. I want to make sure everything's right. All right, looks good. Done. Question 19. Figure 19 shows the spectrum of light emitted from a hydrogen vapor lamp. The spectral lines indicated by the arrows on the figure 19 is in the visible spectrum of light. All right. The following list gives the 4 visible colors that are emitted by the hydrogen atom. Circle the colors that correspond to the spectral line indicated by the arrows. So we have violet, blue, or blue-green, or red. So basically, having a look, we can see that this spectral line is basically, if I really look at this, it's basically, it has the highest wavelength. What does high wavelength mean? It means low frequency. It means it's weak. So which of the following here, from all of these, have the weakest frequency or the weakest one? It's basically red. You know you should have these. Red is the lowest frequency. Violet is the highest frequency because it's the strongest. And blue-violet is basically, the second, and then this one's third, and the last one's the red because it's the weakest. So basically, that arrow corresponds to red, and violet would become that one there. Easy. Explain why the visible spectrum of light emitted from a hydrogen vapor lamp gives discrete spectral lines as shown in figure 19. What a beautiful last question. This question comes up in many of the practice exams that I've done, so I've kind of written it in my basic response, but make sure you answer the question. So I'm going to be, this is what basically it is. An electron in a hydrogen atom, basically in this case, it's a vapor lamp, so a hydrogen vapor lamp. So basically an electron, yep, can only, we know, and basically from my notes, so an electron can only exist in certain orbits. That's what we know. Basically corresponding to discrete energy levels. So basically electrons emit photons when they transition from high to low energy levels. That's what happens. And so they basically emit photons that are discrete, that have discrete amount of energy, basically. So yeah, so we know that overall they have basically energy of photons that are discrete. That's what I want to explain. Now, think about it. Sorry. So if we have discrete amount of energy of photons, we know that the energy of a photon is what? It's given by hc over wavelength. Now, we know this is a constant, but because we know if this is discrete, it means the wavelengths are discrete. So it tells us that basically also the wavelength are certain discrete. So we only have certain discrete wavelengths of light. And that's why we have here, can you see all these wavelengths here? They are discrete. There's only certain amounts that can be emitted of wavelengths, basically. So let me write it, and I'll write you a nice response to show basically whatever I explained. So yeah, it's like a very nice, easy question to pull out in an exam. So 3 marks, wow. And electron, in this case, so we said it's a hydrogen vapor lamp. So in an electron in a hydrogen, basically atom can only exist, we said, so it can only exist at certain orbitals corresponding to discrete energy levels. Electrons emit photons with discrete amount of energy when they transition from high to low energy state. Basically, that's the basics. So yeah, I think that really describes it, but we need to talk about how basically why do we have these wavelengths, these certain wavelengths that are in that spectral line, and that's because, let's write it in a different color, as wavelength of light is related to its photon energy through this basically formula we said equals hc over lambda. A hydrogen vapor lamp basically can only emit certain discrete wavelengths corresponding basically to spectral lines. So corresponding to basically to the difference, let's say, to the difference in energy states, in energy levels. And that's it. I think this kind of goes in very depth for those 3 marks. Yeah. Why do we have a visible spectrum and why we have some discrete spectral lines is because only basically discrete wavelengths are allowed basically to be emitted. Easy. Perfect. That looks good. Next question. 20. I think this is the last question. Yep. So question 20. Some students have collected data on the orbital period and the orbital radius of 5 Saturn moons. These results are shown in the table below. Assume that the moons are in circular orbit. On the axis provided below, plot the graph of the observational data, t² versus r³, include a scale on each axis and draw a line of best fit. Alright, so, okay, let's do that. I mean, they've already done it for us, so we're given these data basically here. They've already done the work for us, so, it's, what is t² written as? It's 10, basically times 10 to the power of 10, and the other one is times 10 to the power of 24. basically. Yep. So that's I cubed. Okay, now let's just basically plot them. Let's see. Wait, we need to first include a scale. So I cubed is going, the most is going 146. So, if I go by tens, is that good? So 10. So if I wrote, so that'll be, means that's 20. Yeah, I think that's good. So 20, 40, 60, 80, 100, 120, 140, 160. That looks good. And what about the other one? So the max it goes is 15. So I think by ones, yeah. So I'll just take, so I'll do it by one. So 2, 4, 6, 8, 10, 12, 14. What am I doing? What? Oh my god, wait. 2, 4, 6, 8, 10, 12, 14, 16. What am I doing? Why did I write 15 there? But, so I want to double check. Yep, 15 is the max. So, yeah, it's good. So that's it. So we include the scale. Now we just need to plot those points. I'm going to plot them. Alright, so the first one's R cubed. So 6.4. That's 10. So if that's 10 there, that's around here. Oops. It's basically around here. I'm going to draw a line, and it's the y value is 0.6. So basically, around here, basically. There we go. Just going to rub that off, and that's it. So that's that point. Next point is 13.5. So 13, so that's 10. So around, basically, around here. 13.5. So 13 and 139. So 1. Alright, so 1. So that's 1. 139 is around here, basically. Done. Next point. Let's look at the one. So 25.7. So 25. So basically 25.7. So if I draw a line here. And 2.66. So 2.66 is around here. Next one. 53.6. So 53, which is here. Around here. And 5.57. So 5.5 is around here. So I'm going to pretty much draw like a color there and rub those off. And 146. So 146 is 145. 146 is approximately here, basically. 15.2. So 15's here. 15.2 is here. That's it. So basically, I've colored those. Now what I'm going to do is basically draw a best line of best fit. And yes, it does pass through all of them. So that's a good thing. Yeah. So that looks great for me. What else is there? So we've plotted them, we've included the scale, and we've drawn a line of best fit. That's beautiful. That should give you that 5 marks. Calculate the gradient of the line best fit drawn in pi. So easy. So gradient, basically m is what? Your gradient is we take 2 points that are nice. For example, basically this point looks nice. And what point nicely passes through the one beautiful point? I'm not even joking. I'll take this point basically because I can't see anything that's nicer, like that's on this crosses. So I'll take those points basically. I mean, not the best thing to do, but yeah, there should be a range of it wouldn't be. You remember they accept a range of answers. So because it's a straight, nice linear line, so I'm going to take those. So 2 basically, it's basically 2 minus 1 times 10 to the power of 10. All divided by basically 20 minus 10, which is basically 10, times 10 to the power of 24. That gives me times 10 to the power of 10, 10 times 10 to the power of 24. That gives me basically 1.0 times 10 to the power of negative 15. That's your gradient. Easy. Use the value of the gradient calculated in part B to determine the mass of the Saturn. Show you're working out. Easy. So if we know that basically our gradient, what did our gradient give us? It's t squared over r cubed. So our gradient gave us t squared over r cubed, which is our gradient. Now, basically, if I look at the formula of Kepler's law, if I just go back to my summary sheet, where are you? Here it is. I know that by Kepler's law, r cubed over t squared is equal to gm 4 pi squared, basically. So my gradient that I got, if I find the inverse, it's going to give me, basically, if I find the reciprocal, so you flip it around, which is 1 over m, it's the same as that, which means that I can substitute basically 1 over m here. And that gives you a beautiful equation, basically, to find m. Because these are all constant, basically. So let's do that. So I'm going to multiply both sides with 4 pi squared. So it'll be 4 pi squared over m, your gradient, equals gm. And multiply both sides by half, so g. We'll get rid of that g from there and there. And so your m, to calculate the mass of Saturn, basically, it's this. Easy, so let's sub that in. 4 pi squared over 6.67 times 10 to the negative 11. What am I doing? Wait. And m is the gradient. What am I doing? Yeah, fully. Yep, so 4 pi squared g, and what's our gradient? It's 1.0 times 10 to the negative 15. Done. So that should give me my answer. So I get basically 5.92 times 10 to the power of 26 kilograms. And that looks good. That answer looks quite good. I hope you guys learned something through this, basically through this video. I hope it kind of helped you understand. And yeah, like always, guys, before I end this video, if you guys please could subscribe and like this video, it'll be a great pleasure. Thank you guys for watching this video, and make sure you take care of yourself. I hopefully see you next time. Bye bye.